Hello students, I am Professor Sagar Sonon. In this video, we discuss about analysis of continuous beam by three-moment theorem. Module Theory of Structure. Topic Continuous beam. Solve example. Type 2. Two span beam with one end fixed and other end supported simple. Example. Calculate the support moment of beam loaded as shown in figure by using three-moment theorem. Span ABC is a continuous beam. Span AB is 4 meter and loaded with UDL 20 kN per meter. Span BC is 5 meter and the 35 kN load which is act 3 meter from B end. In span ABC, A is fixed, B is intermediate support and the C is end simple support. Solution. Step 1. Calculate simple bending moment of each span. Span AB. A 4 meter span AB is loaded with a UDL 20 kN per meter. So the mark D point exactly center of the span AB for calculating maximum bending moment. So bending moment at D equal to WL square by 8. 20 into 4 square upon 8, that's equal to 40 kilonewton meter. Span BC. A 5 meter span BC loaded with 50 kilonewton point load which is act 3 meter from the B support. Mark E point under the point load and calculate maximum bending moment. Bending moment at E equal to WAB by L 50 into 3 into 2 upon 5, that's equal to 60 kilonewton meter. So in here A is a distance from B to E is 3 meter and the B is a distance from C to E is a 2 meter. Step 2. Construct a dummy span. This is the beam ABC. Support A is fixed support. So draw a imaginary span left hand side of the A and mark A0 and their length is L0. It is an imaginary span. So the moment produced at A0 is M0, moment produced at A is MA, moment produced at B is MB, and the moment produced at C is MC. So in this problem, the unknown support moment are MA and MB. And the moment at C, that's equal to 0 because it's end simple support. So this imaginary or the dummy span considered for formation of two equation for calculating a two unknown support moment. Step 3. Calculate area and centroidal distance of simple bending moment diagram, means mu diagram. This is the simple bending moment of span AB. It's parabolic in shape because of the UDL. And this is the simple bending moment for span BC. It is a triangular in shape. So the calculate area and x bar of mu diagram. So first of all, mark figure number 1 and the figure number 2. Dummy span. Area of dummy span A0 equal to 0 and x0 equal to 0. Figure number 1. Area A1, that's equal to 2/3 into L1 into bending moment. 2/3 into 4 into 40, that's equal to 106.67. x1 bar left hand side means L equal to L1 upon 2 equal to 4 by 2, that's equal to 2 meter, and x bar from the right hand side it's R equal to L1 upon 2, that's equal to 4 upon 2 equal to 2 meter. Figure number 2. In figure number 2, A is 3 meter and the B is 2 meter. So area A2 equal to 1 upon 2 into L2 into BM. So 1 upon 2 into 5 into 60, that's equal to 150. X2 bar from the left hand support B equal to L2 plus A upon 3 equal to 5 plus 3 upon 3 equal to 2.67 meter, and x2 bar from the right hand side C point, that's equal to L2 plus V upon 3 equal to 5 plus 2 upon 3 is 2.33 meter. This x2 bar from the left support and x2 bar on the right hand support, which is shown in the figure. Step 4. Calculate support moment of continuous beam by using CLAPEYRON'S theorem of 3 moment. Consider a span A0 AB and applying CLAPEYRON'S theorem. So the equation are m0 into L0 upon I0 plus 2ma into L0 upon I0 plus L1 upon I1 plus mb into L1 upon I1 equal to minus into bracket 6a0 x0 upon L0 I0 plus 6a1 x1 bar upon L1 I1. The flexural rigidity of span A0 AB is uniform, then the value of EI is uniform. Then the equation is m0 L0 plus twice ma L0 plus L1 plus mb into L1, that's equal to minus into bracket 6a0 x0 upon L0 plus 6a1 x1 upon L1, bracket close. In this equation, so m0 L0 is 0, it is for the imaginary span only, and similarly 6a0 x0 upon L0 is 0. This total term we consider a 0 because it's only taken for the formation of equation. So putting all the values a1 x1 L1, so here is one note. Here the x1 value, that's equal to x1 from right hand side. It's taken from the right end B. So the equation is 2ma into 0 plus 4 plus mb into 4 equal to minus into bracket 0 plus 6 into 106.67 into 2 upon 4 bracket close. So the equation is 8ma plus 4mb, that's equal to minus 320. Equation 1. Next, consider a span ABC applying Clapeyron's theorem. MA into L1 upon I1 plus twice MB into L1 upon I1 plus L2 upon I2 plus MC L2 upon I2, that's equal to minus into bracket 6A1 x1 bar upon L1 I1 plus 6A2 x2 bar upon L2 I2 bracket close. When the flexural rigidity EI of span ABC is uniform, then the equation is MA into L1 plus twice MB into L1 plus L2 plus MC L2, that's equal to minus into bracket 6A1 x1 bar upon L1 plus 6A2 x2 bar upon L2 bracket close. So putting all the values A1 x1 bar L1 plus A2 x2 bar and L2 in the equation, here is one note. The value of x1, that's equal to x1L, means left hand side, taken from the left end A, and x2, that's equal to x2R, taken from right end C. So putting all the values, MA into 4 plus twice MB into 4 plus 5, so moment at C, that's equal to 0, equal to minus into bracket 6 into 106.67 into 2 upon 4 plus 6 into 150 into 2.33 upon 5 bracket close. So the equation is 4ma plus 18mb equal to minus 739.41, equation 2. (8ma plus 4mb, that's equal to minus 320, equation 1. 4ma plus 18mb equal to minus 739.41, this is the equation 2. By solving equation 1 and 2, we easily get that the value of MA and MB. So the MA is minus 21.89 kilonewton meter hogging and MB is minus 36.21 kilonewton meter hogging. Step 5. Draw bending moment diagram. This is the continuous beam. Simple bending moment of span AB, parabolic in shape, and simple bending moment of span BC, triangular in shape. So the support moment are MA is 21.89, MB is 36.21, and the moment at C is 0. So joint A to B and B to C. This whole combination of simple bending moment and the fixed support moment is known as net bending moment. So this diagram is net bending moment of continuous beam. Thank you.